If it is an irrotational flow, then what will be happening? So if it is an irrotational flow, the unsteady part, again, it is considering for the unsteady part, because steady part we have already seen. But if it is unsteady flow and irrotational flow, then what will be happen? So as it is an irrotational flow, we know the curl of velocity vector is equal to 0, where the v vector is the grad of velocity potential. The phi is nothing but velocity potential. So as the phi is the velocity potential, so we can write it in this way. So the term del v del t dot dl, the term del v del t dot dl, if you reduce, how it can be written? Rho is a separate, we'll multiply the rho later, but we are just talking about this part. So rho we'll take it later, just multiplying with the parameter. So it will comes in this way, del t of dot dl. What does it mean? Del phi is meaning that I del phi del x plus j del phi del y plus k del phi del z. Okay. So del t of this part. So del t of this part. And you see here, so del t of this part you have to consider. I of this part into dot dl. Dot dl. So dl is I dx plus j dy plus k dz. So if you make the dot product of it, del phi dot dl, it will definitely come del phi del x dx plus del phi del y dy plus del phi del z dz. What does it mean? D of phi. So it will definitely come d of phi. If you reduce this thing, it can be, if it's a continuous function, you can be write it down d of del phi del. Interchange this part, d of del phi by del. So hence, if you multiply with this equation with the rho, so rho will be multiplied here. So what would be your equation? Your equation will comes in this way: dp plus half rho d of v square. So v square means, it, you can write it the v square in terms of del phi square. You can write it simple. Plus rho g dz plus rho d of del phi by del t equal to 0. That's the Euler's equation. If you do the integration, it will comes as a irrotational, for the case of the irrotational flow, unsteady equation, unsteady Bernoulli's equation. But the importance is here, that is the irrotational flow. Now we are discussing about the irrotational flow, whether it is physically possible to maintain irrotational flow. This equation is easy, but whether in reality is it possible to maintain irrotational flow? Because it's a, you see, is a velocity conservative part, conservative field of the velocity is there. Because the V is the conservative field of the velocity. So in that case, if any obstruction is coming, the irrotational flow will be converted into the rotational flow immediately. Irrotational flow will be converted into rotational flow immediately. if there is something is there. Because inviscid flow means that the mu is very less either or no deformation. Because the part is mu del v del x plus del u del y. That is the shear stress equation. Mu into deformation. That is the deformation formula, you get it kinematics. So either this part is becomes 0 or this part becomes 0. If this part becomes 0, then also no effect. Flow may be the irrotational flow. But the matter is here. If the viscosity is neglected or 0, if the viscosity is 0, this kind of flow, viscosity, no viscosity, so inviscid case plus irrotational. If this is combined, we can ensure it much more, because viscosity is always causing some rotationality. Because of the viscosity, what is the viscosity? In between two adjacent layers, there is a difference in the motion. Because of it, there may be chance of the rotationality. There may be chance of rotationality. So to remove the viscosity effect, that means inviscid if you are taking, so mu is nearly to the 0, tends to 0. In such a condition, we can ensure it, and this flow is known as the potential flow. We see one chapter is the potential flow in the fluid in this course, but before just is a conceptually we are telling it that potential flow is nothing but inviscid plus irrotational. But always irrotation can be satisfied. Some factors are there. Because of this factor, irrotationality of the flow may be hampered, may be changed. So what are the factors? We just describe the factor. If there is a presence of any solid boundary. If there is a presence of any solid boundary. So because of the solid boundary, slip will be occur in between two layers, and at the adjacent to the flow, there is a no slip condition, you know. So because of the solid boundary, so some rotationality may be induced. So irrotational flow may be converted into the rotational flow. There are other factors also. We just write it down, some factors name. That is the thermal stratification. That means the layers that separate density. In a fluid flow, the ocean, if you see, if you go for different depth, you will get different temperature. Because of the temperature difference, the density is the difference. And that may cause, for the hot fluid and cold fluid, there may be causing some rotationality. It may induce some rotationality. That is the thermal stratification. Or due to such of any thermal gradient, thermophoresis, or there is a concentration gradient. There may be so many reasons regarding this thing. Thermal stratification. There may be the chance of the shock wave. In case of the compressible flow, if the shock wave front, the sudden and the properties is changing. Suddenly, the supersonic property it becomes the subsonic properties. Sudden change of the properties will be takes place. In that case also, the some rotationality factor may be induced because of the shock wave. Another is the Coriolis effect. If there is a Coriolis effect is there. Coriolis effect. For the ocean, you see the Coriolis effect is the if the frame itself is moving. If the frame itself is moving and over the frame something is sliding, it is experience some another kind of acceleration is known as the Coriolis acceleration. In such cases, some rotationality might be found. In case of the ocean, we can see the Earth itself is a rotating frame. So if you want to go from the northern part to the middle portion or southern end to the middle portion, in such a cases, there may be a deflection. whether maybe in the right side or maybe the left side. Similar kind of those cases. This effect might induce some rotationality. These are the factors which may induce some rotationality in this flow. Now, streamline coordinate, we are talking already, we just give the sense in a streamline. If you take along the streamline, so tangential is a tangential part. It's a unit vector along tangential unit vector, ES, that is along the streamline. And perpendicular to the streamline, EN. EN is the perpendicular to the streamline. There's the coordinate, two-dimensional coordinate system of the streamline. So it's the unit vector along the streamline and perpendicular to the streamline. Unit vector along the streamline and perpendicular to the streamline. What is the, I have already told you, what is the advantage to take such coordinate? Because the velocity will be one-dimensional always. At any instant, the velocity will be one-dimensional always. Because we know the velocity only along ES direction. There is no velocity along EN direction. So if you write it the V, so V vector will be always V of ES. And along EN, there is no velocity. Always velocity is zero. Perpendicular direction. So that is the advantage because it is giving you the sense of one dimension. So two-dimensional flow, you can be converted into the one dimension for the easiness of the problem. You can make the problem easy in this sense. So the same Euler's equation you can derive from the streamline coordinate also, and it is a very easy part. I'm showing you. It's easily we are doing it very first way because already we have seen the Euler's equation, but here. So if you take, it is a streamline. It's a streamline. Okay. So along the streamline, if you take one small element, it's a magnifying figure. So we make it very large. So that is del S. This part is del M. There's a fluid element we are taking. So what is the volume mass of the fluid element? Density. So mass of the fluid element is density into volume. So volume is del S, del N, and perpendicular direction is 1. Let you take because perpendicular to the plane is 1. So rho del S, del N is the mass. So the fluid element is like this one. So there is a, what are the forces acting? Here the pressure force is acting over it. Inviscid condition. Again, it is satisfied also in inviscid condition. So pressure is acting here. That is the P. That is the pressure P. And here the pressure is acting P plus is the del S distance we are traveling. So del P, del S into ds plus higher order terms we are not considering. So that is the pressure. So what is the force? So force is P into del N into 1. Here force is into del N. As the force is acting. So the surface force is, this is the surface force. What about the body force is acting here? The body force is acting, that is the weight. Weight is the mass into gravitational acceleration. So rho del N del S into G. Rho del S del N into G. And if the angle, if you draw a tangent in this line, if you draw a tangent here, so this, with the tangent, it makes an angle theta. So the component of the body force, so along this direction, along the streamline, another component will be here. So the cos component of it. So rho del N del S G cos theta. Is a cos component. That is the body force. So along the streamline, if you do the force balance or equation of motion, if you want to write equation of motion, better to write no force balance. The equation of motion you are going to. So net force, we have to search for the net force. But before going to the net force, what is the cos theta? So cos theta, to find out the cos theta, we take again the same figure. We take it again the same figure just for the clarification about. So it was like this way. This is the del S, this is the del N. Okay. This angle is given as the theta. This angle is given as a theta. So here you take like this one. So if it is a theta, this is also theta. Just parallel. This is a parallel with it. So this part is del S and this part is del Z. Potential difference del Z. So now cos theta can be written as del Z by del S. Del Z by del S. If this del Z del S, if we converge this part in a very small manner, if we converge this part in a very small manner, that means if this element, if we converge this element towards a point in such a situation, it will become d of del of Z. So cos theta, we can replace it as a rho del N del S of dz by ds. So whatever the equation is coming along the streamline, along streamline or S direction, if we do that, so pressure force. So pressure force is acting. What is the pressure force is acting or surface force? Rho dn minus P plus del P del S of dn. That is the pressure force due to surface force plus body force. So body force is also negative. See here, it's a negative term is coming because it is the in this direction, opposite to the streamline direction. So it will comes in negative way. Rho del N del S dz ds. So this is the surface force plus body force is equal to the motion. The equation of the motion, the mass into acceleration along streamline. So acceleration along streamline, it is a unidirectional. So acceleration, the v is the velocity, one dimensional velocity v. So del v del t plus v del v del s. If it is a steady flow, this term becomes 0. If it is a steady flow, you consider this part will not be there. So only part will be there, v del v del s. That is the equation in the along S direction. So what is coming? Minus del P del S. You see this part will be cancelled out, and del S del N is a very small. Del N is tends to 0, del S tends to 0. We are taking it is converged. So all higher order terms also become 0 and this will be cancelled out. So ultimately the equation is coming in this way along the streamline. Rho del Z del S is equal to rho v del v del S. That is the equation. Is the Euler equation along x-axis. So del P del S plus rho del Z, sorry, rho G, one G term is missing here. One G term is missing here. So rho G del Z del S is equal to V del V del S plus V del V del S is equal to 0. That is the Euler's equation is along S direction. It is similar like the Euler's equation. So it can be written as the along S direction. It can be written as the del P or dP. Better to write it dP in terms, no problem. That is because it's a very small pressure quantity, and along in direction we are not considering now that much changes. We're not considering that much changes. Rho G dz 0. If you do the integration about the 2 points, it will comes as it will gives you the Bernoulli's equation similar. So along the streamline, the Bernoulli's equation will be satisfied with the condition, same condition you have to demand. Inviscid gravity is the only body force, steady flow, constant density, and along the streamline. That is the S direction. The same way, the same equation we can derive from it. But the interesting case is along in direction, normal to the direction. So we'll see the normal direction, what is the acting over it. Just I'm giving you the clue. Next day we'll see regarding the in direction. And after that, we'll take another part. This part is very much important. That's why I'm not taking it. That is the vortex flow. And vortex flow is much more related with the perpendicular to the streamline cases. In direction. So in direction is the very much important cases. That is the in direction, normal acceleration. What is the normal acceleration? What is the normal force, normal pressure changes? We'll see one by one. But just giving one clue, as the normal direction, the acceleration is only due to the centripetal acceleration. Or if you consider the frame, whether the fluid is moving, so the frame is accelerating frame. If it is an accelerating frame, as it is rotating, because in a rotating body, acceleration always should be there. So in such a cases, as it is rotating, in such a cases, the frame may be considered as the non-inertial frame. So Newton's laws of motion, you cannot apply this here. You have to introduce the one pseudo force in terms of the centrifugal force, or if you convert it into the inertial frame, then centripetal acceleration can be used. So this part we'll see the next topic regarding here. So here we finish this lecture. Next we'll see the Euler's equation in the streamline coordinate. Then we'll come to the plane circular vortex flow. So interesting, the plane circular vortex flow, how it is happening is the most important thing. In the some physical, some reality example is also there, like tornado, cyclone, how it is acting here. We'll discuss regarding this part also. And free vortex flow and forced vortex flow, all the things we will discuss in this part. So because of this part, this end direction along the streamline is much more important. So here we wind up this part. Next lecture we'll discuss about the end direction.